In question 1, we need to decide how many real solutions there are to the equation 2 cos to the 4 theta minus 5 cos squared theta plus 3 equals 0 on the interval 0 to 2 pi. So I suppose this looks like a classic example of a hidden polynomial in cosine, but it is sensible to pause for a moment. Naively, one might say it's a hidden quartic in cosine, and that's true, because cosine appears as powers up to cos to the 4, but we can make our lives even easier by noticing that because cosine only appears to even powers, we can in fact identify this as a hidden quadratic in cos squared theta, because cos to the 4 is cos squared squared. So obviously a quadratic is easier to deal with than a quartic, so it helps to use this observation to get a polynomial of lower degree. So if we substitute, let's write u equals cos squared theta. Of course, you don't need to make an explicit substitution, but it helps to keep things tidy. The equation reads 2u squared minus 5u plus 3 is 0. Now, can we factorize that? I mean, if not, we'll just have to use the quadratic formula, but this looks like it probably will factorize. If I put a... actually, will it factorize? If I put a minus 3 there and a minus 1 there, I think that should work. We'll get plus 3 and we'll get, minus 5. Brilliant. So that tells me that u has got to be 1 or 3 over 2. Now, we're not done. We mustn't at this point say, aha, there are two solutions, because it's not solutions in u we want, it's solutions in theta. And specifically, some values for u may correspond to multiple possible values for theta, others might correspond to none. So we know that we need either cos squared theta is 1 or cos squared theta is 3 over 2. This we can see straight away, the cos squared theta equals 3 over 2, we can discard, because cos is always between minus 1 and 1, so there's no way we can have a cos squaring to give something bigger than 1. So we see that what we want is for cos squared theta to be 1. That means cos theta has got to be plus or minus 1, and if in doubt, we can count the number of solutions to that from a quick sketch of the cosine graph from 0 to 2 pi. So if this is 2 pi, we see that we take the value 1 at 0 and 2 pi, which crucially are included in our interval, and we take the value minus 1 when we're down at pi. So 3 solutions, the correct answer is C. In this question, we need to find the complete set of values of p for which the equation x squared minus 2px plus y squared minus 6y minus p squared plus 8p plus 9 is 0 describes a circle in the xy plane. So thinking ahead, if we were to try to write this in the form of a sort of manifest circle, something that's in the standard form of a circle's equation, we'd be looking at getting something like this. So we complete the square on the x portion and the y portion separately to get terms like this, and we bring all the x and y independent terms, the constants, over onto the right. So already looking at this, it's pretty clear what the problem could be in terms of getting a circle. Specifically, the thing on the right is meant to be identified with the square of the radius, so if it turns out to be something negative, then that wouldn't really describe a circle. So we can kind of see where this is going. Now, to see what we actually end up with on the right, let's perform the completing the square procedure. So for the x portion, I want x squared minus 2px, so I can get that from an x minus p squared, but I better take a p squared away. So this gives me my x squared minus 2px. It also gives me a plus p squared, which I don't want, so I'll take it off. Similarly for y, I want y squared minus 6y, so I'll have a y minus 3 all squared, but I don't want the minus 3 squared equals 9, so I'll take that away. And then I've still got a minus p squared, I've still got a plus 8p, I've still got a 9 equals 0. So now everything that doesn't depend on x and y, we should bring over to the right. So actually the p squareds cancel. No, they don't. They double up rather. So I get 2 lots of p squared minus 8p. It's the 9s that cancel. So I get this. Now, what do I need for this to be a circle? Well, this is meant to be identified with r squared, which has obviously got to be positive. Notice that the inequality is strict, because if r squared were 0, that would mean that we have a 0 radius circle, which is really just a point, not a circle. So we need that 2p squared minus 8p is positive, but that's dead easy to solve. Pull out a factor of 2p, p minus 4. And then from a simple sketch of a quadratic, which cuts the p-axis at 0 and at 4 and is U-shaped, we see that we're going to be positive when I'm either bigger than 4 or less than 0. So that means the correct answer is D. In this question, we're given 3 statements about a function f. So we're told the second derivative is a for all x. So the second derivative is actually just a constant. We're told that f of 0 is 1, f of 1 is 2, and we're told that if I integrate f from 0 to 1, I get 1. We need to find the value of a. So I suppose we should just go through these pieces of information one at a time and see if we can infer what they tell us. I mean, the fact that the second derivative is a constant seems very, very restrictive in terms of what the function can be, because surely if I have the second derivative, I can integrate that to get the first derivative, to undo one of the differentiations, and then if I integrate again, I'll get the function. Obviously, because these are indefinite integrals we're doing, to undo these derivatives, we're going to have to remember our arbitrary integration constants, r plus c. So integrating once, I see the derivative is ax plus c. Now I'm going to use c1 rather than c, because we're about to do another integral, so there's potentially going to be yet another constant. If I integrate again, I get no derivatives anymore, and I've got a half ax squared plus c1x plus c2. So what we've actually seen is that because of this condition, we know that f has got to be a quadratic function, and moreover, the x squared coefficient has got to be a half a. That's a massive improvement, because up until now, we didn't even know that f was necessarily polynomial. It was a completely arbitrary function. So this is huge progress. Now this information here looks like it might let us start to pin down some of the constants. So f of 0 is 1. Well, if I plug x equals 0 in this, I just get c2, because anything with an x on vanishes. So that tells me c2 is 1. So now I know that f of x is a half ax squared plus c1x plus 1. And then I also know f of 1 is 2. So if I plug 1 in, well, I'm going to get 2, or 1 squared is 1. So I get a half a plus c1 plus 1. So I've just plugged x equals 1 in there. I know that's got to give me 2. Now that doesn't let me figure out both of my unknowns, a and c1, but that's okay. We've got one more piece of information we've not used. Let's use this to eliminate something. We may as well eliminate c1. So I can make c1 the subject. So c1 is going to be 1 minus a half a, at which point we know that the function is a half a x squared. And then c1, we've just said, is 1 minus a half a, lots of x, and c2 we've already seen was 1. So now this is pretty good, because we've only got one unknown in the equation, it's a, and I also have this piece of information that if I integrate from 0 to 1, I'm going to get 1. So presumably that will now give me an equation in a which I can solve. So integral 0 to 1 f of x dx. Remember, when we're doing this integral, although a in some sense is variable, we don't know its value, it's x we're integrating with respect to. So when we integrate, we treat a as a constant. So integrating this term, I'm going to get, well, I have a half, but I get an extra third from integrating the x squared. So I get a sixth ax cubed. From this thing, I keep my constant 1 minus a half a out front, and x integrates to a half x squared, and then the 1 integrates to an x. I need to plug 0 and 1 in. Obviously at 0, because everything's got an x on it, I'm going to get nothing. So plugging my 1 in, I get a sixth a plus 1 minus a half a times a half plus 1. And this is what we know equals 1, because we're told that that integral, the integral 0 to 1 f of x dx, is going to equal 1. So these terms cancel. And if I expand the brackets, I've got a sixth a plus a half minus a quarter a is 0. So this is nice and easy to solve. A sixth minus a quarter, well, a sixth is going to be 4/24. A quarter is going to be 6/24. So we get minus 2/24 a, which is really minus a 12th a, plus a half is 0. So that means a 12th a is a half. So that tells me a is going to be equal to 6. Let's hope that's one of the options. Yes. So the correct answer is F. In this question, we're given two sectors. We're told that they're similar. So they are enlargements of each other, but otherwise they're the same shape. We're told the arc length of the smaller sector is 6, and we're told the difference between the areas of the sector is 21. We're not told, for example, the arc length of this one. We're not told the angles they subtend. And we need to find the positive difference between the perimeters, so the longer perimeter minus the shorter perimeter. Now, I think whenever dealing with any maths problem, it's very helpful to be clear on exactly what the unknowns are in the problem. So yes, r, the radius of the smaller sector, is obviously an unknown, but we also don't know the angle that these sectors subtend, and that's surely going to be relevant. So let's introduce a letter for that so that we can start to get a handle on things algebraically. Let's call it theta. And notice that because the sectors are similar, we know the angle has got to be the same. So now, presumably, if we go through this information, notice we've got two pieces of information for two unknowns, r and theta. We should be able to get simultaneous equations in r and theta, which we can solve. Once we know r and theta, it will be easy to compute the perimeters. So first of all, arc length. Well, we have different formulae for arc length depending on whether we're using degrees or radians to measure our angle. It obviously won't matter. We've chosen to introduce the letter theta, so whether we choose to measure that angle in radians or degrees won't affect the perimeters or the difference between the perimeters, as long as we're consistent with any other formulae we use. For example, if I use the radians formula for the arc length, I've then chosen to measure theta in radians. If I then use the degrees formula for sectors, that's not going to be good. So we've got to be consistent, but otherwise we're free to choose. We may as well use the radians system because then the formula is nicer. So in radians, the arc length is going to be r theta. You must memorize that because there's no formula booklet for the TMUA. So from that, we learn the arc length of 6 is equal to r theta. So that's one equation, and it's a very simple one too. We're also told that the difference between the areas is 21. So we know that the area of a sector, again, we're going to use the radians version of the formula to be consistent with what we just did, is a half r squared theta. So that tells us that a half, well, we better do the big minus the small to get a positive difference. So a half r plus 3 squared theta, that's the area of the bigger sector, minus a half r squared theta, that's the area of the smaller sector, is equal to 21. So let's call that equation 2. And now, presumably what we can do is eliminate, for example, theta by noting that theta is 6 over r, and we can plug that into equation 2. I think it's better to eliminate theta because r appears in a more complicated way. So we'll tangle up the algebra more if we do it the other way around. So theta equals 6 by r in equation 2. Well, let's see. A half times 6 is going to be a 3. So I get 3 lots of r plus 3 squared over r minus 3 lots of r squared over r, so that's just r, is 21. So now I guess it's sensible to multiply that through by r to get rid of the fractions. Clearly in doing that, we get what looks like a quadratic. Notice this is r squared because there was already an r there and I've now multiplied through by r. This looks quadratic, but actually when we expand out the brackets, I think what we're going to find is that the quadratic terms will in fact cancel through. So that's even better. We're going to get a simple linear equation in r, which will have one unique solution. So the r squareds cancel, bringing the r's on the right, we've got 3r is 27, so the r is 9. And then remember, theta was 6 over r. So that means theta is 6 divided by 9, which is 2/3. You might be a bit worried seeing at such a small angle, but remember we've chosen to measure in radians. 2/3 is tiny when measured in degrees, but it's a pretty decent angle when measured in radians. Okay, so now this is really easy. If we want the perimeter, we've got to take into account the arc length and also the straight edges. So for this one, we now know that r is equal to 9. So we've got a 9 and a 9 and a 6. Over here, r plus 3 is going to be 12, so we've got a 12 and a 12. To find that arc length, I can just use my radius is 12 times my angle is 2/3. So r theta for the r and theta for that sector. So 12 times 2/3 is going to be 8. So what have we got as the difference then? Well, we do the perimeter of the big one, 12 plus 8, minus the perimeter of the small one, 9 plus 9 plus 6. So that is 32 minus 24, which is 8. So the correct answer is C. So I mean, this looks like quite a daunting problem, but once you start introducing letters to represent the unknowns and converting the information given into equations, as is so often the case for TMUA problems, this is just a boring simultaneous equations question. In this question, we're told that the terms xn of a sequence follow this rule. So given one term, you do that term plus p over that term plus q to generate the next term. And we're told p and q are real numbers, though we're not told what they are. And given that x1 is 3, x2 is 5, and x3 is 7, we need to find the value of x4. So I guess what we need to do here is pretty straightforward. Presumably, this information is going to let us try to figure out what p and q are, and then once we know p and q, I can use this result along with the fact x3 is 7 to generate x4. So let's jump in. I mean, the fact that x1 is 3 doesn't really tell us anything because x1 is the starting point. It doesn't come from the recursion. But I then learn by plugging x1 equals 3 in that x2, which we're told is 5, must be equal to x1 plus p over x1 plus q. So I guess that tells us that 15 plus 5q is 3 plus p. So we may as well make p the subject. So p is going to be 12 plus 5q. Let's put that in a box and give it a name. We'll want to come back to it in a moment. Playing exactly the same game with x3. So we know x3 is 7, but by plugging x2 in there, we know that's what we've got to get. So x2 is 5, so that means 5 plus p by 5 plus q has got to be 7. That tells me, multiplying through, that 35 plus 7q is equal to 5 plus p. We might as well again make p the subject as it appears with a coefficient of 1. So then I get that 30 plus 7q is p. Let's give that a name. We'll call it b. Now surely, because a and b are equivalent expressions for p, we can just equate them and solve to see what q has to be. Then we can plug back into one of those to find p. So this looks really easy now. So equating a and b, what do we learn? We learn that 12 plus 5q has got to be the same thing as 30 plus 7q. Collecting, let's say, the q's on the right and the numbers on the left. On the left, 12 minus 30 is minus 18. On the right, 7 minus 5 is 2 lots of q. That tells me q is minus 9. And then if I come back in A, I learn that p is going to be 12 plus 5 lots of minus 9. So that's 12 minus 45, which is going to be minus 33. So that's brilliant then. We now know that x of m plus 1, remember it was xm plus p, but we now know p is minus 33 over xm plus q, but we now know q is minus 9. So if I want to find x4, I just need to use the x3 is 7 in that result. So x4 is going to be 7 minus 33 over 7 minus 9. So 7 minus 33 is going to be minus 26. 7 minus 9 is going to be minus 2, so that gives 13. So correct answer is H. In this question, we're told that the integral of x from log base 2 of 5 to log base 2 of 20 is log base 2 of m. We need to find m. So I mean, looking at this, it's very easy to get tricked into thinking it's a scary integral of a log or something because all the logs floating around, but it's not. The actual integral is just of x, which is dead easy. It's only the limits which are logarithmic. So we can compute the integral of x. Let's do that. Let's plug the limits in, and then let's think about what we can do next. Obviously, in any question to do with logs, we should be very, very alert to the possibility we want to use log rules. So plugging in those limits, I get log base 2 of 20 squared by 2 minus log base 2 of 5 squared by 2 equals log base 2 of m. Okay, so I just said we want to make sure we're using log rules. It is also important to make sure you don't hallucinate a log rule that doesn't really exist. So notice here that the square is not on what's inside the log, it's on the whole of the log, right? It's the log itself that's being squared. So there is a log rule that says that if you do log of something to a power, you can pull the power out, but there is not a log rule for a log or a power of a log, where the power acts on the log itself. But students very frequently will sort of hallucinate log rules that would be useful if they did exist, and it can lead to all manner of trouble. So specifically, the log rules that we really have at our disposal are the one I already wrote, and also that log of AB is log of A plus log of B. Well, what can we do? I mean, because we've not got anything with a power inside the log, I guess this is all we can do. Log base 2 of 20, of course, because 20 factorizes, perhaps I can use this rule to some effect. So I know that log base 2 of 20, well, 20 is what? It's 4 times 5. So log base 2 of 4 plus log base 2 of 5. But that is brilliant news, because log base 2 of 4 is obviously 2, because 4 is 2 squared. And log base 2 of 5 is common to this thing. So when I square this, I'm going to get some cancellation with that. So this looks pretty promising. Sorry, let me erase that from an earlier attempt. So let's do this then and see what happens. So we're going to get, well, if I square this there, I'm going to get 4 plus log base 2 of 5 squared plus 4 log base 2 of 5, and that's still all over 2, minus log base 2 of 5 all squared over 2. That's the stuff that we know is equal to log base 2 of m. But then this cancels this, and what we're actually left with is 2 plus 2 log base 2 of 5 is equal to log base 2 of m. So I've done the division through by 2 there. So this is pretty good. We're certainly getting there. Well, if I now want to isolate m, I'd better just do 2 to the power of both sides. So I learn that m is going to be 2 to the 2 plus 2 log base 2 of 5. There's obviously some scope for simplification here, specifically if I can manage to rewrite it in a way that says 2 to the log something. But I can do that really easily, break off the 2 squared, and then for the 2 to the 2 log base 2 of 5, write that as 2 to the log base 2 of 5 squared. So I've just used the n log a is log a to the n log rule, the first one I mentioned, but to bring a power in rather than out. So that there is 4. That there is going to be 5 squared, which is 25, because obviously the exponential and the log are each other's inverse. So we get 100. And so that means the correct answer is F. In this question, we need to find the finite area enclosed by the line y equals 0, so that's obviously just the x-axis, and the curve x squared minus 4 modulus of x minus 12. So when we're looking for an area bounded between a curve and the x-axis, our mind should turn to integration. But I think before we actually write down any integrals, it's a good idea to draw a simple sketch. For instance, we need to be very clear on whether the area we're after lives above or below the x-axis. In terms of whether we have a plus or a minus sign, there might be bits of the area above, bits of the area below, and that will require careful treatment. So this is the function we want to focus on. It's a little bit complicated because the modulus is not on just the whole function, it's on one piece of it. So what's very useful when dealing with a complicated looking modulus function, this is covered in lesson 3 of our TMUA primer course, but I won't assume you've seen that here, is to use the piecewise definition of modulus. So when I write modulus of x, what I really mean is x if x is at least 0, and minus x otherwise. So if x is negative, I negate it again to get rid of that minus. So I can apply that idea here. I can see that x squared minus 4 modulus x minus 12 is going to have 2 formulae. So when x is at least 0, the modulus of x is just x, so it reads x squared minus 4x minus 12. If x is negative, then that modulus x actually becomes a minus x, minus minus makes plus 4x on that term there. So it's really easy to write down a piecewise formula, and now we can produce a sketch. So, first of all, what happens at x is 0? Well, at x is 0, both of our formulae agree. They say that we're down at minus 12. Of course, it's not important that this sketch is to scale. Now, for x positive, we're obeying this one. So maybe we should look for any x-intercepts. That certainly seems important, particularly when we're looking at areas bounded with the x-axis. So what we're going to have to do then is solve this equation to find x-intercepts. But any solutions we find with a negative x value will discard, because this formula is only valid when x is at least 0. So this, does it factorize? I think it probably does. X minus 6, x plus 2. So naively, we might think there's a minus 2 solution, but because we've just used the version of the formula which is only valid for positive x, that gets discarded. We see there's going to be an x-intercept at 6. So this is a quadratic. It's obviously U-shaped. It cuts at 6. It would then extend the other way, but we don't need to worry about that because we're using the other formula for the negative x. Notice that I've also not worried too much about what the gradient's doing here. I'm not necessarily claiming it's flat, but I think for our purposes, doing this integral, it's not really going to make a lot of difference. So then for the other half, we know we still start at minus 12. In terms of any intercept for that one, we're now solving the equation x squared plus 4x minus 12 is 0. That factorizes very, very similarly. So now we get x equals minus 6 and x equals 2, but now it's 2 that we discard because this version of the formula is only valid for negative x. So we then get our other x-intercept over at minus 6, and we've got something like this. So the parabolas may not be flat here. There might be a bit of a cusp where the formula changes. You could investigate that by differentiating, for example, but for our purposes, that's not really necessary, because now what we can see is we've got essentially these two equivalent areas. So if I want the area, what I better do is integrate this piece, remember, is coming from the negative x formula. So to get that bit, I'm integrating from minus 6 to 0 of x squared plus 4x minus 12. And I better put a minus in front of that because of the fact that the area is below the x-axis. So the integral is going to give me minus the area. Now I could similarly write down the integral from 0 to 6 of this thing. Alternatively, if you're feeling particularly clever, what you could do instead is notice that clearly by symmetry, the two areas are the same as each other, and you could just take double this. So just put a 2 there. Let's do that because this is a very time-pressured exam, so we'd like to save time where possible. So what have we got then? We've got minus 2 lots of x cubed by 3 plus 2x squared minus 12x. So I've just performed the integral on these terms. And then we go from minus 6 to 0. So at 0, we just get nothing. And then at minus 6, well, let's see. Minus 6 cubed, well, 6 squared is 36. So 6 cubed is going to be 216. So we get minus 216 by 3 plus 2 lots of 36 is 72. And then minus 12 times minus 6 is going to be another 72. Now, numerically, I think 216 over 3 is itself 72 again, if you just perform that division. So actually in here, these things cancel, and we just get a 72. Well, that's a minus 72, but then there's another minus out front here to cancel it. So we get plus 2 lots of 72, which is 144. So if you had, rather than having that 2, also done this integral, which is the contribution from the other piece there, you would have just gotten the same thing again, but we made our life a little bit easier by doing it all in one go. So the correct answer is going to be E. In this question, we're told that a geometric sequence has first term A and common ratio R, where A and R are both positive integers and R is greater than 1. I guess if R is a positive integer greater than 1, that really means it's at least 2. So we can note that down. R is at least 2. A is at least 1 because it's positive and they're both integers. We're told that the sum of the first n terms is denoted by Sn. Well, that's just standard notation. And we're told that the terms of the sequence obey this equation for some positive k. We need to find the smallest possible k. So surely we should use that we actually know a formula. We should certainly have memorized it. There's no formula booklet for the TMUA. We know a formula for the first n terms of a geometric sequence added together. So we get that the sum of the first n terms is a1 minus r to the n over 1 minus r. So surely I can plug that in here to give me a simple equation relating a and r. We may be a bit worried because there are in principle two unknowns, a and r, but we've only got really one equation to work with. So hopefully what we'll see is that one of the variables secretly cancels. Let's see. So S30 is going to be A1 minus R to the 30 by 1 minus R. S20 is going to be A1 minus R to the 20 over 1 minus R. And S10 is going to be A1 minus R to the 10 over 1 minus R. So this is brilliant news. For one thing, yes, the A's cancel. We can safely divide through by A without worrying about division by 0 because we know that A is positive, so it's at least 1. And we can also cancel these denominator factors of 1 minus R through. So this thing has simplified tremendously to an equation which is just in R. So then these cancel as well, and I guess what I'm left with is R to the 20 minus R to the 30 is K1 minus R to the 10. But then it gets even better because I can obviously pull out on the left a common factor of R to the 20, which gives me a factor of R to the 10 that I can cancel on both sides. So I certainly know it's safe to cancel through this because if R is at least 2, there's no way that that factor is going to be a 0. So we've actually just found, without any serious work, an expression for K. We know that K is going to be R to the power of 20. Okay, but obviously we then want R to be as small as possible. If R is a positive integer greater than 1, the smallest R could be is 2. So that means that the minimal value that K could possibly take is obviously just going to be 2 to the power of 20. The bigger R is, the bigger K is. You can see that clearly from this equation. So the correct answer is B. In this question, we're asked about pairs of functions f and g, which we're told satisfy the following. So we're told f minus g is always 2 sine x, and f times g is always cos squared x for all real numbers x. And we're asked across all solutions for f, what's the minimum value that f can ever take? I mean, everything about this equation, I think, is screaming at us that we ought to take a simultaneous equations perspective, even the phrasing all solutions for f. So while it might seem a bit strange, what I'm suggesting is view these two things here as simultaneous equations where f and g are the variables. I know they're really functions, but they're the things we want to find. And we're going to basically treat these things like constants because yes, they're functions, but they're functions which we know. So these are the known things, these are the unknowns. So it's an unusual perspective to take, at least for A-level or IB or equivalent maths, but the question seems to be indicating it, so let's just take that perspective and see what happens. Well, if I want to make f the subject, if I want to solve these equations for f, I might as well start by using equation 1 to eliminate g, so we can see that g is going to be f minus 2 sine. I can plug that into equation 2, so I just replace g with this. So I get f of x times f of x minus 2 sine x is equal to cos squared. So this really is a quadratic in f. It may seem slightly perverse to have a quadratic where the variable is itself a function, but it's no different to when we have a hidden quadratic having substituted something. It's a perfectly reasonable situation to be in, really. So we can view everything other than f as if it's a constant coefficient. And then I guess this isn't going to factorize very nicely, but we can use the quadratic formula. Now, students often worry about using the quadratic formula when the coefficients are not really constant. So of course, sine x is not really a constant, it varies depending on x. But thinking back to the proof of the quadratic formula, it just comes from basic algebraic rearrangement of the equation by basically completing the square. So that means the proof nowhere used the fact that the coefficients were constant, and therefore it's totally fine to use the quadratic formula to make the quadratic's variable, whatever it may be the subject, even if the coefficients are not genuinely independent constants. So we can use the quadratic formula to see that f of x, now it looks like we're going to get something a bit horrible, but because the question's been set, something good must happen, right? They're not going to set something impossible. So b squared is going to be 4 sine squared minus 4ac. Aha, there's the good thing. So in our square root, we get sine squared plus cos squared essentially, and we know that sine squared plus cos squared is 1. So this looks really good. So inside that square root, well, I've got 4 lots of sine squared plus cos squared, which is just 4 lots of 1. Obviously, the square root of 4 is 2. So what we get is that f of x is going to be, dividing through the 2, I get sine x plus or minus 1, because this is itself 2 over 2 makes a 1. So there are 2 possible expressions for f which work. That's not surprising, because the question says across all solutions, implying there's more than 1. But obviously, if I'm looking for the minimum value that any possible value of f can take, I'll clearly do better by taking the minus root. So I'm going to choose to take the minus to get my minimal value. That gives me sine of x minus 1. And then because, of course, sine varies from minus 1 to 1, the smallest this is going to be, let's call it f min, is going to be when sine of x is minus 1. So that's minus 1, which is minus 2. So the correct answer is E. So I think this is one of these TMUA problems where many students will have been so scared off by how unfamiliar the basic mathematics in the problem looks. But once you jump in and just start applying familiar ideas like simultaneous equations, quadratic formula, the problem melts to nothing very quickly. So the hardest bit is really having the courage to actually jump in and start trying the obvious steps. In this question, we're told a sequence of translations, so just translating left, down, up, right, sliding the graph along, is applied to x cubed, and we need to decide which of the following graphs could be the result of this translation or this sequence of translations. So it's always helpful when dealing with a problem to ask yourself, what is it that actually makes the problem complicated? And I think the apparent complexity here comes from the fact that I could do some horizontal translations, then some vertical translations, then some more horizontal. So it is to do with the fact that we could jumble up the order of each translation. That seemingly introduces infinitely many possibilities. But if you think about it, just picture the act of translating something. Obviously, translating, say, right, then up, then right, is the same as just doing the total of the right translations, then the total of the up translations. Translations don't interfere with each other. So although it seems like there are infinitely many ways we can jumble up the order of horizontal and vertical translations, we can clearly see just by considering the geometry that all possible sequences of translations can be captured by just doing a horizontal translation, which just captures whatever the total horizontal translation your complicated sequence would otherwise have done. So a horizontal translation, let's say by A, followed by a vertical translation, which just captures the effect in total of all the vertical translations you otherwise would have done. So we don't need to worry about the order of the various translations. So let's say the vertical translation is by B. Now, we know how to perform both types of translation algebraically. So to translate by A horizontally, I replace every x with x minus A. If you want an overview of graph transformations, including a slightly different perspective on them that can help with composition and some more advanced transformations, do take a look at lesson 3 of our TMUA primer course. So we know that we can do the horizontal translation by replacing x with x minus A, and we can do the vertical translation by just adding b to the overall thing. So now I can just expand this out, compare it to these options, and see whether they are achievable. So expanding out the brackets using binomial expansion, we get, I guess, this for the x minus a all cubed, and then we've got plus b. May as well collect like terms, although actually that's already happened, right? Automatically the like terms have already been isolated, so x cubed, x squared, x and constant. Now let's look at 1, 2 and 3. Are there going to be choices of a and b that would give rise to any of these? Definitely not 3, because there's nothing that we can do that would change our x cubed coefficient from being 1. So anything involving 3 gets ruled out. That's pretty useful. We're down to pretty good odds at this point. And then I guess for the others, let's just see what we can do. So if we did want to get a match with 1, by looking at the x squared coefficients, we'd need to choose a equals 1. But then if we choose a equals 1, the x coefficient doesn't work. So we would want an x coefficient of 9. We've already had to pick a equals 1 to get the x squared working, but now the x is not working because we get 3, we want 9. So no x coefficient wrong. So there's no way we can make 1 work. That rules out B and also E. And then what about for 2? So for 2, well, we want minus 9x squared. So I guess that means we better choose A as 3. What happens if we choose A as 3? Well, the x squared coefficient is then going to be 3 times 3 squared, which is 27. That's what we want. And then over here, I've got minus 27 plus B. And as long as I then pick, because I want -3, as long as I then pick, I guess, B to be 24, that clearly does work. So just by going through coefficient by coefficient, we see that it is possible to choose A and B to build option 2. So only 2 was possible, and the correct answer is C.